Hello there, wind power students. Dr. Shragi here. Welcome to the second module of our course. And today we're going to be starting a module that's kind of all about weather patterns and weather systems and so on that kind of give us an overview of the context in which we're going to be making wind power. And our first lecture today is about what we call the geostrophic wind. Let me give you a little hint here. The geostrophic wind is going to be an approximation. It is a way of kind of estimating what the winds are doing at any given location. A really simple way of coming up with a surprisingly good way to estimate what the winds are doing at any given location. But it is just an approximation. It builds on the things that we learned towards the end of the last module. For example, in the last module we were learning about the forces that were at work in the atmosphere, and there was a fairly good list of them if you remember this particular slide from last time. And for the purposes of large-scale horizontal winds, covering large areas of the country or so on, the forces that make the most difference are going to be these three: the pressure gradient force, the force of friction, and Coriolis force. So if we could really just get a handle at any given time of what those forces were doing, we could talk about how the winds are changing or accelerating in the context of Newton's second law, like we learned about in the last module, where we kind of had this way of we started with F equals ma, and we pulled the m over to the left-hand side of the equation so that this was force per unit mass was equal to acceleration, and we said it's actually the net force, where that was the sum of a bunch of different forces acting on, in this case, an air parcel at any given time. And I had typeset it all up like this so that it was like force 1, force 2, force 3, but now we can actually put some names on this. We could say one of those forces is pressure gradient force, one of those forces is Coriolis force, and one of those forces is going to be friction. In fact, we don't even need this F1, F2, F3 thing anymore, because our book has been actually giving us notation as to what we mean, and we'll use P vector to mean the pressure gradient force. We'll use C vector to mean the Coriolis force, and we'll use F vector to mean the force of friction. I'm not loving those notations. That's not a standard thing that you would find in an atmospheric science textbook or something like that, but I get it. It makes sense. Okay, so we have these three forces that together determine the net acceleration on an air parcel. The pressure gradient force, the Coriolis force, and the frictional force, all per unit mass, but that's kind of saying we're working with density and so on. Okay, so this basic idea, though, that we can take an air parcel, we can start talking about the forces that are at work producing an acceleration, as we would see on the right-hand side of this equation. Or, if you think about what an acceleration is, it's a change in velocity with respect to time. You may or may not be a person who's comfortable with writing things like calculus way like that, dv dt, change in velocity with respect to time, but that's okay. We're gonna get rid of some of these terms anyway. Okay? Now, we, in the last module, had learned about those forces, but we also started talking about when multiple forces are acting on an object, how they work and how they cancel each other out, or how they work in the same direction, or so on. And we started talking about situations like, you might remember, where we had that airplane, just to have stolen a slide from the last module here, where, like, when the plane was cruising, the thrust pushing the plane forward was equal to the drag pulling the plane, well, slowing the plane down, I guess is a better way to put it. And since the force forward was equal to the force backward, there was no acceleration acting on, there was no net acceleration on this airplane, so its velocity was not changing. Well, let's make that same sort of assumption for our air parcel. Now that's a little bit tough of an assumption to make. Lots of weather patterns are about how things are changing, but let's just say for right now, we're going to be making a fairly simple assumption here. We're saying things aren't changing. We're not changing how the contours of pressure, the isobars, are distributed, so we're not changing the pressure gradient force. We're not changing the latitude at which this air parcel is in a big way, so we would need to worry about the changes in the Coriolis force. We're not doing anything like moving it over surfaces with different roughness where we'd have to be worried about the friction changing. Let's just say that the forces are constant right now, so that they're going to not be changing. There's not going to be a change on the motion of the parcel. We can kind of cross all that stuff out and just say, we're going to keep the air parcel not changing its velocity. There's no net acceleration. These forces add up to 0. This is going to be the kind of it's going to be an approximation that the atmosphere is in some steady state, where, at least at this moment, there's no acceleration acting on this air, its velocity is not changing, dv dt is 0, and that means that these forces have to add up to 0. My pressure gradient force, plus my Coriolis force, plus my force of friction, have to all add up to 0, in just the same way that when that airplane was cruising, the thrust pushing the plane forward, and the aerodynamic drag slowing the airplane down had to add up to 0. That's what the pilot is doing as he adjusts the throttle, is he's getting it so that the plane continues at a constant speed and isn't continuously speeding up or continuously slowing down. Okay, I think at least as a first place to start, I can live with this assumption that my wind is not changing. Okay, so all right, I want my 3 forces that I'm working with in this on this air parcel here. I have an air parcel drawn as a little blue circle here on a map of Nebraska. And I labeled 3 forces on that air parcel there. There's a red vector that's supposed to be the pressure gradient force. And there's a green vector that's supposed to be the Coriolis force. And there's a black vector on there that's supposed to be friction. And I want those 3 to add up to 0. That's not really such a hard thing for a computer to do. Computers would sit there and actually add up, exactly the component in the x direction and the component in the y direction of each of the vectors, and it would actually determine, but you know what the deal is? Human brains don't work that way. Human brains are really hard at working with things that come in 3 competing ways, okay? It's an interesting little bit of psychology, but human brains don't do this well. Okay? If I'm going to be trying to make something I can understand with my puny human meteorologist brain, I'd better make this somehow simpler than this. Because as much as I'd really like to be able to take all these forces into account, the truth of the matter is I have a mortal brain, and I can't do that. Okay, a computer can do it, a computer can tell me important things, but if I just want to make an approximation, a geostrophic approximation, I am going to need to make this situation simpler. And that's what we're going to be doing in part 2 of this lecture. But before we get there, I want to ask a couple of background questions that kind of tie back actually to the first module of the course, but will be information that you kind of need to remember as we move forward into the next part of this lecture. All right? So here's question 1. When the forces acting on an object add up to 0, it means that the object blank, A, experiences no motion, B, experiences no acceleration, or C, has no kinetic energy. What does it actually mean if we can actually say the forces add up to literally 0 that are acting on that, the forces acting on that object add up to 0? Make a choice from those 3 options, and then we'll get some feedback before you move on to question 2.